remember when we needed implicit differentiation, when you had an equation and we had difficulty expressing y as a function of x, but we had an equation with both x and y, and we found that it's much easier to just go ahead and differentiate the whole equation such that the derivative of one side equal to the derivative of the other side, and then isolate and solve for dy dx. Recall that? That's what we did 2 semesters ago in Calculus 1. I don't think we did any implicit differentiation in Calculus 2. So we're going to pretty much do the same thing, but we're going to define it slightly differently. So let's start with the supposition, and we're going to say that suppose I'm going to create another function, uppercase f, and f of xy defines y implicitly as a differentiable function of x. Okay. In this case, well, it will be y equal f of x, but sometimes we won't be able to express it this way. But the point is, the function now f of x, y, actually f of x, y equals 0 for all values of x. In other words, x is x is a variable of y, and both x and y now play a role or variables of the big function f. Notice that we set f in a standard form. It's an equation that all the terms are collected to the left side and the right side equals 0. Okay. So, and here we need to say that for all x in the domain, of f, like so. Actually, that will be the little f right here. Okay. So, we're going to do the following. We're going to differentiate implicitly. Differentiate f of xy equals 0 implicitly. And what we get is del f del x, and this one will be dx dx, plus del f del y dy dx equals 0. We want to solve for dy dx. Okay? So solve for dy dx. So dy dx equals the following. Move this part. Again, let's write here dx of course equals 1. So del f del x would be now on the right side, it would be negative, so it would be negative del f del x, and we need to divide by del f del y. And we'll write short notation, del f del x, the partial derivative will be f sub x, and del f del y will be f sub y, like so. Okay, and this is a little two-variable implicit differentiation rule. So, to give an example, you may recall this curve from Calculus 1. Given the equation of the curve, and it's a famous curve, x cubed plus y cubed equals 6xy. Okay? Who said so? Willie?
Yeah.
The volume of the car. Right. The one that he was challenged by, he challenged, René Descartes challenged Fermat to find the tangent. Remember, René Descartes was interested in finding the tangent to this curve. He couldn't find because he did not know enough calculus. Fermat, however, knew calculus ahead of his time, and that's why some people consider him as Fermat's father of calculus, in addition to of Newton, Leibniz. And if you took my calculus 1, then we discussed this quite a bit, and we had a project on the topic. No, it was the group ahead of you, actually. Come to think about it, not you. I mean, we did it too, but right. I do variation of the theme whenever I teach Calc 1. Anyway, what we need to do is find dy dx. Okay? So let's go to the solution. Okay? X cubed plus y cubed equals 6xy is the volume of the card, just for the record. Volume is leaf in Latin, and it looks like this. If you recall, it looks like that, and we want to find the derivative for this, and so what we'll do now is slightly different than what we did in Calculus 1. In Calculus 1, we went ahead and differentiated left side and right side, but now we defined f in the standard form. So our f has to equal 0, so it will be x cubed plus y cubed minus 6xy equals 0. Okay, don't forget this step. The tendency is to forget that. And now we're going to say, okay, del f del x, we need that, or f sub x. The derivative of this function with respect to x is rather easy, 3x squared minus 6y, right? Del f del y is likewise 3y squared minus 6x. So there is a beautiful symmetry here, and dy dx will be simply based on this, f sub x, negative f sub x divided by negative f sub y. So negative, and it will be 3x squared minus 6y in the numerator, and 3y squared minus 6x. We just swap x and y to get in the denominator, and that's it. So it's a different way to obtain the same result as we did in Calculus 1. Volume of the card. Yeah, volume. F-O-L-I-U-M. In Latin is a leaf, or the leaf of the card. Based on, if you review the history of these two mathematicians, you can sense a measure of dislike between the two, Fermat and Descartes. But Descartes was somebody who did research on Descartes. He said that he was not a nice person necessarily. He was not. He looked down at people. He had his nose up in the clouds, and he thought that his God gift to humanities in a way. And he definitely looked down at Fermat. And Fermat was the better mathematician. But Fermat did not do work in a formal manner like Descartes. Descartes was very formal, very prim and proper, and he followed every theorem with detailed proof and all of that. Anyway, let me expand that, okay? So let let me go beyond this point.